Good morning, and thank you to everyone for attending. I know it's pretty early on a Monday morning, so I appreciate it. As Sonia said, my name is Kyle Morgan. I'm a research fellow at Nanyang Technological Institute, where I work on turbid coral reefs and in a Singapore context, urban coral reefs. Today, what I'm going to present, though, is sort of a background of my last or previous postdoctoral work on the Great Barrier Reef, which was really around the sort of paper that we had out earlier in the year, where we looked at trying to provide and develop a quantitative model of reef growth to look at how changes in reef geomorphology can influence the spatial extent and spatial patterns of living coral habitats. So what I'm going to do today is really look at a number of different field case studies and trying to give an overview of how we collected this data and some of the key findings from each of these field studies, because these really provide the foundation for a lot of the sort of assumptions that we built into this reef growth model. So just before I start, I want to recognize NERC. This was funded as a NERC large grant in collaboration with the University of Exeter, and in particular Chris Perry, who I know gave a talk last month, as well as colleagues at James Cook University in Townsville. So when we kind of envision what a coral reef system is and the environmental conditions under which corals live and under which they thrive, we really have this kind of idea typically of these clear water, or as some people call them, blue water coral reef settings. So the water is typically oligotrophic, which means it's nutrient poor. We have low suspended sediments and sedimentation rates on reefs. And collectively, these kind of drive these kind of really ambient conditions where we have very good visibility and high light conditions on reefs, because surface sunlight can penetrate deep into the water column. If we have sort of a healthy reef state, what we do see is coral reefs dominated by high coral cover, high three-dimensional complexity on reefs, as well as diverse coral assemblages. And we see that coral growth and we see reef development occurring to sort of an excess of 30 meters in water depth. And so in these sort of ideal conditions, it's very easy to use sort of traditional visual sensors-based surveys to evaluate coral reefs, as well as more traditional approaches in remote sensing to kind of map their spatial extent and their ecological zonation. I felt fairly easy. However, turbid coral reefs are really the complete opposite of these clear water systems, and they sit at the other end of the environmental spectrum. They're characterized primarily of really poor visibility, and I have here sort of less than 5 meters, but if you've been lucky enough to dive on a turbid reef, particularly the reefs around Singapore, you'll know that there's a number of days where you cannot see your hand in front of your face. And the reason for this is because we have these reefs characterized by high suspended turbidity, high suspended terrestrial sediments, as well as dissolved organic matter that scatter and absorb light as it penetrates through the water column. So overall, the conditions on reefs are very low and light, and as a result, we have very distinct coral compositions. So we typically corals that are more stress tolerant. They can handle sort of daily fluctuations in environment. Their coral morphologies are better adapted to shed excess sedimentation that's deposited on their surfaces. Then we also see taxa that favor sort of heterotrophic feeding rather than sort of conventional autotrophy. In terms of reef zonation, what we also get is a vertical compression in the maximum depth range of these reef systems to sort of the upper shallow waters, less than 10 meters, because beyond that we have very low light conditions for reefs to develop. Okay, so they're a very different sort of and unique sort of setting that we don't really know much about. And the reason for this is because we can't typically apply a lot of these kind of traditional approaches that we use in clear water and turbid settings. They just don't work. When we think of visual sensors, when we also think of remote sensing, the turbidity really impairs a lot of these approaches being used. So they still remain really poorly explored coral habitats. And just to put into context what I'm kind of sort of talking about, if we look at this section of the Great Barrier Reef, we can see that the reef system is hugely immense. In some places, the outer shelf can be up to 180 kilometers off the mainland coast, and we can broadly define the reefs within that based on their relative position to the mainland. And so the reefs that we're kind of working on and that I'm talking about today are these nearshore reefs really stuck in very close to sort of these coastal environments near the sort of main Australian coastal continental landmass. Okay, and despite this sort of close proximity to the coast, we don't know too much about them. As I said, we don't really know much about their sort of spatial extent. A lot of them remain sort of uncharted because we can't easily identify them in satellite imagery. We also have very few records of their general coral ecology and the communities on these reefs. And in terms of their geology, we only have a few sort of case studies really where we have reconstructed their past growth histories and their long-term development. So collectively not having these kind of baseline parameters for these systems, it makes it very difficult to try and interpret how these reefs are going to respond to increased anthropogenic stresses like declining water quality, as well as climate-related impacts. So to kind of get at a lot of these kind of questions and fill some of these knowledge gaps, we've been working in an area of the nearshore central Great Barrier Reef in Australia, which is becoming a bit more well-known, called the Paluma Shoals Reef Complex. And this is located in Halifax Bay, which is just north of Townsville, if you know the area. And what we have here is quite an extensive network of reefs that occupies turbid waters with high sediment resuspension from the seafloor that's driven largely by wave energy. And what we see is a range of these reefs, and they occupy different stages of evolutionary development. So we define that by their relative elevations to water level. So we have some that are close to the shore that have attained sea level and become semi-emergent at low tide, whereas some of these offshore reefs are still remain submerged and are actively accreting and growing up towards sea level. So what we initially wanted to do is collect and constrain our understanding of these reef systems. And we really comprised a sort of holistic field campaign to try and understand these reefs in more detail. And so the key thing that we first did was to try and look at the reef morphology and to map the spatial extent of reefs in these turbid waters. And this involved hours of doing single beam acoustic survey tracks up and down, mowing the grass across these reef structures. And we racked up about 130 kilometers in survey tracks. So using this data, we then derived a digital elevation model, and we got a good understanding of where these reefs are and their sort of general morphology. We then supplemented these geophysical surveys with hours of drop-down video transects across the main reef sequences. And from that video, we then extracted over 4,000 benthic still frames that we used to quantify different ecological metrics. So we looked at the different benthic cover and substrate cover. We looked at coral cover, the different composition of coral communities. And we also looked at reef structural complexity. And because we had this really detailed digital elevation model, we were able to depth calibrate all of this ecological data. The second phase of the project was to get an idea of how the reefs have grown in the past, and then of the past coral communities that actually were driving vertical rates of reef accretion and carbonate accumulation. So to do this, we undertook quite an extensive reef coring campaign where we percussion cored, which basically involves bashing a large pipe through the reef structure, and we penetrated the entire Holocene reef sequence at all of these locations. So we collected 31 cores in total, and using radiocarbon dates of various coral material from within those cores, we were able to look at what were the ages when these corals started to form, what are the sort of general rates of vertical reef accretion in these environments. And then we had a PhD student, Jamie Johnson, who did an amazing job working on these cores, analyzing individual coral fragments, and he actually worked through over 85 kilograms of coral fragments throughout the study. So he did this to sort of reconstruct these sort of paleo coral communities on these reefs. So in terms of the geophysical mapping, after we completed this exercise, what we saw was that we had these really extensive reef structures sitting offshore within these turbid waters. And so the aerial photo on the top left actually is quite recent, and when we undertook this field work, we didn't see many of these structures, so we didn't really know what we were going to find. And you can see from the digital elevation model constructed on the bottom that these ridges are very extensive, they're linear in shape, and they're kind of orientated perpendicular to the shore. We also can define sort of two sets of reefs, so we have the sort of offshore shore detached reef structures, which are typically still below sea level, and so they're still actively accreting up towards sea level attainment. And then we had the sort of more well-known sea level attained shore attached reefs that are welded to the coast, these sort of intertidal sand flats. The areas surrounding these reefs was generally flat and featureless and covered with sort of a muddy seafloor sediment, and the depth gradient as you move offshore sort of generally gets deeper. When we looked at the sort of living coral communities from the drop-down video transects that we use, again, we were quite surprised. These reef structures were supporting immense coral cover, very high three-dimensional structural complexity, and a variety of coral genera that we don't typically associate with these really turbid and low light conditions. And so average coral cover was about 38% across all of the survey footage, but over huge areas, a localized coral cover was between 90 and 100%. And you can see in the footage some of the incredible coral cover that we did see. Particularly what we were surprised about is a lot of this branching acropora and tabular copper, which you don't associate with turbid settings. Being able to depth calibrate this ecological data to our digital elevation models, we could see then too, what we were getting is really rapid transitions in coral communities that occurred with depth. And when we plotted the distribution of dominant coral taxa across depths, we could see that each taxa occupied a very narrow and a very niche sort of depth range. So we had Montiparas occurring in more shallow waters, but not at depth. Acroporas too preferred sort of shallow water habitats, but below wave base at about 1.5 meters LAT. Whereas Turbinaria we found more commonly on the reef slopes, sort of more muddy, sort of lower light conditions at about 3 meters. And Porites were sort of less, they were sort of at deeper depths, but with a bit more of a depth generalist throughout the surveys. Okay, so we saw really clear transitions and really rapid transitions in where these corals grow. So we were able to use the spatially resolved benthic data and this digital elevation model because they were depth calibrated to do some sort of clustering hierarchical analysis and delineate distinct turbid coral habitat types. And this was basically based on the benthic cover, looking at whether we had sand or whether we had rubble, the different types of corals in those habitats, and also the different growth morphologies, as well as their reef structural complexity. We were then able to construct a nice clear habitat map for Pluma Shoals Reef Complex, looking at their spatial extent and spatial distribution. And it was clear that these habitat types, again, stuck within these very defined and very distinct depth ranges, and transitions between these habitats occurred very rapidly. In terms of reef chronology, our cores also provided a really nice story and set up a lot of the work that we use and inputs that we put into our reef growth model. So essentially, we can see here on the right-hand side a typical core from Pluma Shoals, and we can see from the radiocarbon analysis, radiocarbon dating, that these reefs are fairly young in terms of a geological context, so sort of less than 2,000 years old. During that time, we've had very rapid reef accretion at rates that far exceed sort of clear water environments. And we've also had continuous vertical reef accretion, with these reefs actively growing over time, and a lot of these still in a phase of active reef accretion and carbonate accumulation. What's key, and again, you can see this in the core quite clearly, is that throughout their growth histories, the reefs have developed continuously under high rates of sedimentation. So the sediment matrix throughout the core is very muddy and is consistent to what we see on today's reefs. However, when we pulled all the data together and we looked at our varying reef accretion rates, what we then saw as a trend was that reef accretion was variable with depth. And when we compare these reef accretion rates, and you can see this in graph B here, the mean accretion rates correspond to living coral assemblages at equivalent depths. Okay, so where we had high rates of reef accretion, we typically had high rates of framework production and coral growth. And sort of more shallow locations where we had more patchy coral cover and more stress tolerant, exposure tolerant, and slow growing corals, this attributed to sort of lower rates of vertical accretion as reefs attained sea level and became impacted by wave events and things like this. So this figure is really just kind of summarizing what I just said. We have these very clear depth distribution of different habitat types, and these correspond to depth variable rates of reef vertical accretion that we saw in our cores. And from the work that Jamie did reconstructing the paleo coral communities, we also saw that the paleo coral communities had very similar depth distribution as living coral centers, which implied that there had been very little modification between past and present corals within these turbid settings. Okay, so we don't really expect that there's been any sort of major disturbance, environmental change that has in fact impacted the coral community compositions from past through their entire growth history to what we see on reefs today. So one of the key drivers that is driving this kind of vertical shift and rapid shift in habitat is really to do with light attenuation from the surface down into the depths in these really turbid waters. We have high amounts of sedimentation and suspended material being constantly reactivated by wave processes. And we can see from data collected from Paluma shoals on the left-hand side, under high turbidity conditions at 4 meters water depth, we have about 100% of surface light being completely removed. Even under sort of low turbidity conditions, so these periods of sort of calm weather where we have relatively higher light, even at 5 meters water depth, 75% of surface light has been removed. So if we compare that to a sort of a hypothetical clear water reef, that's kind of at equivalent depths of what's happening at sort of 20 meters, okay? So the light is decreasing very rapidly, and as it's doing so, it's compressing the vertical depth distribution of these corals and these habitat types into a very narrow depth range. The other kind of interesting thing that we see associated with light, although it's constricting vertical growth, it also shows that it could actually be really important for the tolerance, for making these turbid corals more tolerant to coral bleaching in periods of high thermal heat stress. And we had a chance to sort of test this in 2016 because we already had this prior really detailed ecological data set from these turbid reefs on Paluma shoals. And then we had this very large heat event that came through and caused widespread mortality on the GBR shelf. So when we went out soon after and resurveyed the ecological transects, we saw that there was very little difference or the little impact of coral bleaching in that survey data from late 2016. And so after analysing about 11,000 individual coral colonies, we only noted bleaching to occur on about 173. And of those corals, most of it was sort of some sort of minor paling or some sort of partial mortality, non-focal bleaching. So the kind of hypothesis is, and this is widely sort of talked about now, is that the high turbidity is reducing UV stress on the corals during these times of thermal stress and mitigating some of those effects that drive coral bleaching. So obviously coral bleaching is a major climate related impact, but in these systems where we have very limited and very low light conditions and we have very strong depth controls of coral communities, sea level changes is obviously also going to be a significant threat to these habitat types, and that may drive changes in habitat as we increase the relative water depths above reefs. So a big question still remains is how will higher sea levels influence both future habitat extent as well as the reef bioconstruction, so how reefs grow and develop and their morphology changes through time. So we know now that global sea level rise is projected to increase water depths above reefs. It's just really a matter of by how much. And of course, we can see negative consequences for both the marine biodiversity and habitats in these systems, but also for a lot of the geomorphological functions that reefs provide. So when we talk about wave protection and reef habitat and structure in these kind of coastal settings. So we do now currently have like a current and quite a good understanding of the magnitude, but also the specific drivers that are causing ecological decline on reefs, so coral bleaching, localized human impacts. But what is kind of of interest and what we don't really know about so far is how will the spatial extent of future reef habitats change over sort of geomorphological timescales, because these are naturally dynamic systems. They're actively accreting and changing the underlying surface morphology, which is bound to have effects for the organisms that are living on top of them. So the two reasons why we don't really have that kind of baseline information at the moment is because for many reefs, the species compositions that are on modern day reefs and living reefs are highly modified from what they were when the reefs were formed, or the main organisms that actually provided the carbonate production to drive vertical reef accretion. They've been so heavily modified by disturbance that they don't really reflect the historical paleo kind of coral communities. What we also see is that there's very few sites globally, and this is not just turbid reefs, this is reefs in general, where we have these kind of high resolution, temporally resolved data sets of past reef growth side by side with coral communities and assessments of living ecological habitats to actually put into models to see how these reef look like. Quite often geologists and ecologists work in separation, and these data sets don't often aren't available for the same location. So by developing a lot of this field data from some of the studies that I just showed you, we do actually have a chance and a unique opportunity here to incorporate some of that material and some of that information into trying to model future trajectories of these turbid reef habitats. So the idea was to really use that to incorporate into this model a predictive sort of reef growth model to look at future reef behavior and change. And the reason why we can do that is because firstly, we have long-term coral communities that have existed and grown under continuously high sedimentation rates. So there hasn't been any major environmental change occurring between past and present conditions. We also have very strong correlation between both past and present coral assemblages and the ecological communities that drive carbonate production in these systems. We've had consistent reef accretion rates with within these depth-constrained habitats, and there's likely has been an absence of major disturbance, and based on the sort of resilience of corals to thermal stress, there is likely to be in the next 100 years an absence of major disturbance from these kind of large-scale bleaching events. And so we can kind of confidently use our data to sort of model future predictions of habitat cover. So the idea was to produce this sort of quantitative depth habitat controlled predictive reef growth model. And what that model was really meant to do was to simulate reef growth through time, but also under different scenarios of sea level rise. So we can increase the depth above reefs, see how the reef morphology changes, as well as the habitats that occupy the reef. Okay, so we can look at changes in habitat extent as the reef morphology grows, and I've also put in here shrinks because we can also shrink these reefs back to the initiation phases. And then we can start to infer some ecological metrics, things like coral cover, rugosity, based on what we know from the living coral communities on today's reefs and the habitats that we see and we've collected in our field data sets. So as I said, we can reverse these models back into time and shrink these reefs back to their early initiation to kind of validate them against our core records, which we know is how these reefs have sort of grown in the past. So to do this, we kind of made this, we started with our digital elevation model of the seafloor, and we assigned each grid a label corresponding to either the absence or the presence of reef. So each of these cells can then grow vertically using number 2, so a depth vertical growth rate or reef accretion rate. And then it uses this kind of principle that as the reef grows, the underlying surface morphology changes and the environmental conditions on that grid cell change, and that will then influence the benthic composition of the grid. Okay, we can then allocate each depth grid based, we can allocate each grid based on its depth a different habitat type to kind of look at different habitat distributions at different time spaces. So after the model was formed, we wanted to first validate it using our reef core data set. So we ran it backwards from its present day reef morphology, basically until all the cells were removed on the seafloor. So we shrunk the reefs back to basically their early initiation phases. And we did this pretty successfully, and we can see the different colors with the different main reef structures, and the graph represents the remaining reef area as you move back through time. eventually hitting zero. And what we saw is when we did this, most of the reefs initiated between around 1400 to 700 years before present. And these aligned really closely with the basal ages of the cores that we collected from these locations. So it was in very good agreement between the modeled and the core data set that we can use core rates to actually grow reefs back through time, because what they represent is the net result or the net product of reef growth. They incorporate all the carbonate production, all the carbonate erosion, sediment inputs, all into a nice tight sort of cell that we know occurred. So we don't need to model those things individually. We can look at past rates of reef growth to actually apply to these models. And so by doing this, it actually gave us confidence that if we can grow them back to how they grew to the initiation, then we can actually start to project and predict future morphological change if we use them under similar environmental conditions and similar sort of timescales. So this is some of the model outputs in terms of the spatial distribution of reef morphology for not only the reefs, but also the surrounding seafloor areas. So we modeled in a 3D complex, 3D environment, the entire Paluma Shoals reef complex. And you can see on the GIF there that early reefs started growing around sort of 500 years before present, and they were really characterized by these sort of isolated patch reef environments, and they took a little while to get going. So it was only till about 200 years before present they were growing very slowly, and they finally made it above sort of sea level, above the seafloor at about 1.5 meters. And it was at this time they then began to expand and then really start to rapidly vertically accrete. If we project sort of morphological changes going forward into the future, what we can see is that these reefs are going to increase the accommodation space. They're going to fill their vertical accommodation space by plus 300 to 500 years into the future. They're going to become sea level attained. They're going to develop reef flats and then start to switch to lateral reef growth as the main function of reef development. But what does this mean for the reef habitats themselves? So again, if we look at these same time slices of 500 years before and after present day, we see that habitat configuration on these turbid reefs is very dynamic over geomorphic timescales. We see very large and clear shifts in the spatial extent and also the configuration themselves of the habitat types. Starting off around 500 years ago, where sediment tolerant corals with some of the main dominant taxa that initiated these reefs. And this agrees with what we see in our core records. It was only around sort of 200 years ago, again, when they start to build higher off the seafloor, get more access to light and out of that sort of sediment resuspension zone, that we get a switch to shallow water habitat, things like really 3D complex Acropora and Montipora coral colonies. If we project these habitat changes further forward from present day, so around 300 years into the future, we see major declines in what we now have as the turbinaria coral habitat. And we see a much further expansion of this really productive shallow water habitat. So under static sea level conditions, particularly at offshore sites, we're going to see more productive corals forming in the next sort of 200 or 300 years. However, that rapid kind of accretion associated with these highly productive coral communities, by the time we hit plus 500 years, these offshore reefs are going to start hitting sea level, as I said in the previous slide. And what we are then going to start seeing is shifts in coral cover decline on those reef tops. And we're going to see higher abundances of rubble and macroalgal substrates increasing as we kind of transition to this reef flat setting at these offshore locations. So the previous two was kind of showing a spatial interpretation of how these reefs will change both in the past and into the future. And this is kind of compiling all that data to show how dynamic reef habitats can be and how we can see relative dominance changes in the habitat as we go from the past to the present. Okay, and so I think some things to point out here are just the sort of the, originally this yellow line, age 6, which is our sediment tolerant corals. They were initially really abundant in the early phases of growth, but as we move and the reefs become more complex and move towards sea level, they become less dominant and really just are present around the sort of reef slope at the base of reefs. If we look at turbinaria coral habitats, which is the green line, we see a peak sort of around present day, but this is going to drop off. In terms of, if we again look at reef flats, which is the red line, but they weren't obviously very abundant initially because reefs were very just taking off. But as we grow them forward into the future and sea level is attained by the reefs, then we're going to get a larger dominance and a higher proportion of Goniastria reef flat habitat forming on these sites. So this was about when we had a static sea level, but if we look at what this means in terms of increasing sea level, because sea level rise will increase into the future, if we model these reefs and project them out to 100 years into the future under different scenarios of sea level rise, so RCP 4.5, which is sort of a moderate estimate of sea level rise projection of about 5.5 millimeters per year, and then RCP 8.5, which is a more high emission, but unfortunately more likely scenario of sea level rise of 7.5 millimeters per year, we see very different changes and different patterns and what we expect the habitats to do in response to changes in reef morphology and the depth of the reef substrates themselves. Okay, so I know there's a lot to look at in this figure, but I just want to kind of summarize some of the sort of key findings. So if we look at 100 years at the static sea level, we're going to see very increasing reef flat development, basically, as these reefs hit sea level and start to prograde laterally. We're going to see increased shallow water habitats, so really productive reef systems, which is the light blue color on the left panel. This is going to increase under static conditions. If we look at RCP 4.5, the reefs that are shore attached, so close to the coast, which is the middle panel, reef flats are going to then transition likely to shallow water habitats. So we may get a transition of what is typically a low coral cover habitat to a high coral cover and high complexity dominated habitat in the future. The offshore sites, we may see reefs becoming increasingly submerged as water depths rise, and we may see declines in the same shallow water habitat at these offshore sites, and these locations being dominated by more sandy, muddy, kind of sediment tolerant taxa. Under the high emission scenario and probably the more likely scenario, again, at these shore attached sites, we see more substrates being potentially recolonized by shallow water habitat. And at the offshore sites, what we see is shallow water habitats, so the productive habitat, being really restricted to only the high nodal elevation points on these reefs. So we're going to see typically generally losses in coral cover and reef complexity as the waters get increasingly inundated and submerged. Turbinaria, which is the green habitat, is going to become the dominant habitat type. And although we have high coral cover in these situations, they are very monospecific, and we actually reduce the coral diversity on these reefs quite significantly. What's happening on the reef slopes is because these areas are going to be increasingly dropped out of the photic zone, the reef slopes suggest that we're going to see an expansion of non-reef building substrates, so sands and muds around these sort of deeper reef areas. Okay, so I'm kind of running out of time. So just to sort of summarize, basically that the main points from the sort of paper that we had out is that what we've been able to demonstrate from the model is that we can actually model and actually quantitatively analyze reef functionality over different geomorphic timescales, which is really an important aspect to look at when we're looking at projecting ecological communities through time. So basically, as under this principle that as the reefs build vertically or become increasingly submerged through sea level rise, the environmental conditions essentially on reefs are altered. So we get differences in wave exposure, light regime, sediment resuspension, and also the emergence times of corals. So we're naturally going to get a shift in the coral cover and the species composition as reefs evolve and move naturally through their evolutionary stages. Okay, so we may see quite dramatic changes in coral cover that maybe occur naturally in the absence of any sort of major disturbance or anthropogenic sort of inputs or climate-related effects. So the timing and the magnitude of when we will see these habitat reconfigurations is largely controlled firstly by the rate of sea level rise, so how fast water is inundating these systems. Two, the vertical reef accretion rate, which is how fast the reefs are growing vertically and if they can keep up with these rates of sea level rise. And three, the local turbidity regime. We're going to see more pronounced effects occurring on sites that have higher turbidity because there is lower light availability, and reef communities are likely to be more vertically compressed. And again, so just to summarize the kind of scenarios, if we project under this RCP 4.5 scenario, we could, and this model projects that we may see re-establishment of high coral growth on some of these reef flat areas at the shore attached reef sites. But a large part of this is dependent on whether these substrates now are actually suitable for coral settlement to occur. Okay, so a lot of them are covered in turf algae, macroalgae, and they have high amounts of sediment bound into the algal turf, which may actually impede recolonization of those zones. So although the model projects that, whether this actually occurs is dependent on other sort of external factors. In terms of rapid sea level rise, or RCP 8.5, the model's projecting really the same sort of effects, but sort of more exaggerated, and very negative impacts on coral cover generally as the euphotic depth shallows. So this is particularly going to be more at the shore detached or off reef sites, where coral diversity is likely to decline as turbinaria takes over, as it can kind of deal with the more deeper water muddy conditions. And also these kind of deeper water depths on reefs are going to push a lot of these kind of reef slope corals below their photic limits, these ones that are currently at sort of 3 to 4 minutes, and push them into sort of non-reef building sort of substrates. However, understanding this kind of dynamics on turbid reefs is important because, as I said, these are potential climate change refugia. They show tolerance to coral bleaching and thermal stress. And so it's critical to evaluate how the future habitats are going to respond to these natural shifts in reef geomorphological development, which are occurring, but also to sea level rise. So I just want to finish by saying thank you to obviously the funders, NERC, but also to my current funders and to all the collaborators who worked on this quite field intensive project. Thank you.